Okay, class, I'm sorry I can't be with you today. I've been sick most of the weekend, but we're going to try to finish off 1002 today, and then you'll have some time to work on your WebAssign and on FRQs. You do have 3 new FRQs due this week. I do not think we'll be meeting on Tuesday because of the mission trip retreat, so I wanted to go ahead and get this done for us today. If you remember the last time we were talking, we had started talking about series. Series are just sequences that are being added together, and we said that one of the big things that we're going to be worried about is how do we determine if a series converges. And we will come up with 10 different tests or 10 different methods on determining if a series converges or not. The first we talked about was geometric series, and a geometric series is one that has a common ratio. You've seen that before, where each term is created by multiplying by a specific number, the previous term. And we discovered that if the common ratio is less than 1 in absolute value, then that there is it does converge, and we can find the sum to be the first term over 1 minus that common ratio. Now, we can use that to figure out how to write this 0.08 as a ratio of 2 integers. That's just another way to say how can we write that as a fraction. Okay, now if you think about what does 0.08 with a line over it mean, 0.08080808, it just keeps repeating just like that all the way through. So what we can do then is we can think of this as, well, these first 2 numbers, that's 8 over 100, and the second 2 numbers, we get that by adding 8 over 1000, and the next 2 numbers is 8 over 10,000. Whoops, I think I made a mistake there. That should be 10,000 there, and this should be 100,000 here. Notice what's happening each time to our denominator. Our denominator is going up by a factor of 10 to the second power. We went from 100, that being 10 squared. This is 10 to the 4th. This is 10 to the 6th. So then we have a common ratio here of 1 over 100. So that makes this a geometric series. Since it's a geometric series, we should be able to find the sum if the common ratio is less than 1. Well, the common ratio here is 1 over 100. So then our sum would be the first term over 1 minus the common ratio. Well, what was our first term? Our first term was 8 over 100. So if we write 8 over 100 over 1 minus 1 over 100, if we simplify that, that's 8 over 100 divided by 99 over 100, which becomes 8 over 99. And if you use a calculator, you'll see that 8 over 99 does become the repeating decimal, 0.0808. So that's just an example of how it could be used. Most of the time you would not be asked to do something like this. You would be asked to do something where you have a series and you have to determine, is it geometric? If it is, does it converge or diverge? These properties are true for all series. If we've got 2 series that we know the sums for, A and B like we have here, then the sum of a constant times that series is the same as C times that sum, which makes sense. If we've got the sum of 2 series and we know the sum of each one, we can add the sums, and that's the sum of the 2 series combined together. Similarly, if they're being subtracted, we can subtract the sums. So these are just common sense properties. I'm sure if you think about it for just a second, it makes sense that if we know that the sum of this set of numbers is A, the sum of this set of numbers is B, the sum of the 2 sets together has to be A plus B. And the same thing for subtracting. Now we're going to look at our next test, and this test is actually for divergence, to determine if a sequence is diverging. So it doesn't tell us that one is converging. It's a way we can tell if it is diverging. So let's just think for a second before we get into these. Suppose we know that our series B sub n, or suppose we know that our series capital B converges. What does that mean? Well, if we know that B converges, we know that we can find the sum. That means if we take the 48th partial sum, and then we take the 50th partial sum, and we take the 95th partial sum, all of those are getting closer and closer to some number, and that number is called B, what it converges to. Well, let's think about what that means. How do we get from the 48th partial sum to the 50th partial sum? We do that by adding the next two terms, by adding the 49th term and adding the 50th term. So another way of thinking of this is, as we add terms to this more and more, what's happening to the terms themselves? What's happening to little b as n approaches infinity? Well, as n approaches infinity, since all of them are approaching one specific number, each individual term is getting smaller and smaller. Therefore, b sub n is approaching 0 as n approaches infinity. So that's what we say here with this, this first thing here. If it converges, then the nth term, the limit on the nth term has to be 0. Now, that doesn't mean that if the limit is 0, then it converges. That's not what that says. This says if the series converges, then the limit has to be 0. But we can take the contrapositive to that, and that's what this one is here. That's the test that you'll be using from time to time. If the limit is not 0, then the series must diverge. So anytime we can take the limit as n approaches infinity of the terms, if the limit is not 0, then we know it diverges. If the limit is 0, that doesn't mean it has to converge, but if the limit is not 0, then we know it does have to diverge. So we're going to look at a few examples of this in the next slide. When we look at this series here, this is going to be 2 to the 0 plus 2 to the 1 plus 2 to the 2 plus 2 to the 3 plus, and so forth and so on. So what happens if we look at the limit as n approaches infinity of just this individual term of 2 to the n? Well, n is going to be getting larger and larger. 2 to the n is going to be getting larger and larger. So this limit is going to be infinity. Since this limit is infinity, then we know that the series diverges. We know that by the nth term test. See, if the limit is not 0, then the series has to diverge. So we know that this series has to diverge because of the nth term test. Now, if we look at this second one, what do we know about it? Well, it's a little bit more complicated to take the limit here. We can't really do any algebra to this, but we can think about it that n factorial and n factorial are essentially the same number there. So when we take this limit, if we were to test it with several numbers, larger numbers, we would see that this limit is 1/2, which is not 0. Therefore, we can again say that this series is going to diverge. Okay? And then the third one on this page, what about the limit as n approaches 1 of 1 to infinity? Well, we know that the limit as n approaches infinity of 1 over n, n's getting larger and larger on the bottom, so this limit is 0. So it's a 0, but that doesn't tell us anything. That means it's inconclusive. And we will learn how to test something like this later on, because the limit sometimes when it's 0, sometimes when the limit is 0, it will be a convergent series, but sometimes it will be a divergent series. Again, going back to what we said here, if the limit is not 0, then it diverges. We can't take the opposite of that, saying that if the limit is 0, it converges. It doesn't work that way. That's the only test that's like that, so you've just got to be very clear on that, that's what you're looking for. This slide is an example of how we can use some of the techniques we've learned here to solve a real-life application problem. We're told that a ball is dropped from a height of 6 feet and begins bouncing as shown in figure 8.7. The height is 3/4 for the previous bounce. The height of each bounce is 3/4 the height of the previous bounce. Find the total vertical distance traveled by the ball. Hopefully you can see that this is a series because we're adding up a sequence of numbers. Also, by the simple fact that we're told that we can find the total distance, we are told that it is a convergence series. If you'll read a little bit closer, I would imagine that you could pick up with right here that says the height of each is 3/4 of the height of the previous bounce. So that means our first time it drops 6 feet, then the next time it drops that far down, then the next time it drops the same distance but times 3/4. And suddenly, hopefully you see that what we're trying to do is we're trying to add up a geometric sequence, because each successive term is found by multiplying the previous term by 3/4. So we've got a common ratio of 3/4. So if we use our formula, we get 6 over 1 minus 3/4, which is 6 divided by 1/4, which is 24. But we're not finished at that point. The 24 is only talking about the distance that the ball has dropped each time. Notice the 6 feet is how far it goes down. The 6 times 3/4, if it's talking about the up, then we don't have anything to talk about the down. So I'm going to say that each of the numbers in our sequence there are just the down beats, just how far down it falls. So we need to go back and figure out how far up it bounces each time. Well, the only difference between the up sequence and the down sequence is it doesn't rise 6 the first time. On the up sequence, it starts off at this distance, 6 times 3/4, and then the next one is 6 times 3/4 times 3/4. So we've got the same common ratio. The only difference is we've got a different first term. Our first term is 6 times 3/4 divided by 1 minus 3/4, which becomes 6 times 3/4 divided by 1/4, which becomes 6 times 3/4 times 4 over 1, and we can cancel the 4's and get 18. So while the ball bounced downward 24 feet, it bounced upward 18 feet for a total of 42 feet. I encourage you to go back and look at all of this again if you have any questions, because we will not have time to go over all of this in class again. We will try to start up on Wednesday in 10.03.